All right, hi everyone. We're going to go ahead and get started with our 1 o'clock press conference. This is new science from the 2018 Kilauea Eruption. So our panelists today are Kyle Anderson from the U.S. Geological Survey and Adam Soule and Chris German from the Woods Hole Oceanographic Institution.
Good afternoon, and thank you for coming. So I'm going to be talking today about just a tiny subset of the remarkable science and observations that are coming out of the 2018 eruption and caldera collapse at Kilauea Volcano. I'm going to talk a little bit about some material that's been recently published, and then also some intriguing new lines of investigation. So the 2018 activity at Kilauea was the largest eruption in more than 2 centuries, and that's important because Kilauea is one of the best monitored volcanoes in the world, and as a result, it's really one of the world's premier natural laboratories for volcano science. Caldera collapses are potentially hazardous, but very few have been observed globally. In fact, before the activity at Kilauea this summer, just 7 since 1900. So the observations from this summer have given us some really intriguing new insights into the triggers and mechanisms of caldera collapses, not just at Kilauea, but potentially globally. Magma storage volumes and conditions at Kilauea and the relation to caldera formation, the causes of some of Kilauea's quote-unquote small summit explosions, and the connection between the summit and the volcano's rift zones. So activity at the summit in 2018 at Kilauea was driven by a high rate of magma evacuation from the summit towards the volcano's lower east rift zone. That's the high rate eruption that you're going to hear more about in later talks today, and some of my colleagues from the USGS are here as well to answer questions about that part of the eruption. So magma was draining rapidly from the summit, and that caused the summit magma reservoir to deflate very much like a balloon. That caused the lava lake at the summit to drain, and it drained very rapidly. The video on the right is a series of thermal images taken from May 2nd to May 8th, showing the lava lake draining at a rate of about 50 meters per day. The photo in the bottom, or the video in the bottom that I'll show you, shows that lava lake. You can see it right there. This is a series of images taken from the Hawaiian Volcano Observatory on the rim of the crater, or the caldera. And what you're going to see is a series of overflows before the eruption started. You're going to see the lava lake now drained from sight, a series of explosive eruptions that took place from mid-May to late May, and then broader collapse of the caldera. So the explosions that took place at the summit in 2018 were actually the largest that had happened there since 1924. So conceptually, we tend to think of volcanoes exploding when magma intrudes into the volcano, it pressurizes, and that causes an explosion. But as I just showed, the opposite was happening at Kilauea. In fact, the summit was draining. The summit was deflating. So what caused these explosions? Well, conceptually, it's been believed for many years now that these kinds of explosions are caused by the interaction of magma and groundwater. So the idea is that as lava drains in the lava lake, as the summit depressurizes, that causes cooling and cracking of the conduit around the lava lake. It allows groundwater to filter back in, interact with the magma, and cause explosions. However, there are a number of new observations and models from the eruption this summer that suggest that maybe something else was happening. So these include gas emissions, groundwater models, and other observations. And they suggest that, in fact, groundwater did not play potentially a significant role in driving the explosions at Kilauea's summit this summer. Going back to 1924, that calls those interpretations into question as well, although that's, of course, more speculative. So one interesting question is, calderas form when magma drains, magma drains from summit magma reservoirs. That causes depressurization and then collapse of the roof rock into the reservoir. That's what causes a caldera collapse. So a fundamental question then is, where's the magma stored at the summit, and how much is there? These are questions that have obvious implications for hazards, but are actually surprisingly difficult to address in many cases. So using the remarkable data from the summit this summer, we're able to, I think, place some really improved constraints on some of these questions. So the animation I'll show you on the right is a simple movie showing what we've been able to achieve by inverting or using the data from this summer to estimate magma storage location and volume. The broader structure here is Kilauea caldera, and within that is the collapse that formed this summer. So if we'll play this movie, this is where we estimate, conceptually speaking, magma likely to be beneath the summit. I'll start back from the beginning again, because what's really interesting is you can see that that storage location is very nicely located right beneath the collapse structure that formed. We estimate that the volume of that magma is probably on the order of a few cubic kilometers at least. It may be a little bit larger, and it was probably stored at a couple kilometers beneath the caldera floor. Now, of course, this is a very idealized model. You can see that. We don't actually believe that magma is stored in these spherical bubbles in the crust. We can't really capture the finer details of magma storage with these kinds of models, but these are still really useful because they allow us to address some really interesting questions. For example, how much did that reservoir contract before the roof rock started to fail? That's an important question that has important implications for caldera collapse mechanics. And at Kilauea, it looks like that was fairly small, probably less than just a few percent. We can also look at how much magma we think exited the reservoir during the entire eruption, and if we know how big the reservoir was to first order, we can ask, well, how much magma is still located there? Did the reservoir completely drain? And the answer is almost certainly not. There's almost certainly still magma beneath the summit at Kilauea. So one question to ask then is, how does collapse take place? Was it sudden and catastrophic? Was it incremental? Was it gradual? And there are observations from other volcanoes, from Yakajima or Bardabunga, for example, in Iceland, that suggest that these calderas can collapse episodically in a series of collapse events. However, those volcanoes, those collapse events were not resolved or observed in anything like the detail we've seen at Kilauea. So a lot of great science came out of the Bardabunga eruption in 2014 and 15, but that caldera was actually covered by hundreds of meters of ice, whereas at Kilauea, we could actually watch these things taking place from the rim of the caldera. So it's a pretty amazing opportunity. So this is a three-dimensional rendered view of the summit before the collapses started to take place. And then this is what it looked like at the end of the summer after the eruption stopped. So the question is, how do you get from point A to point B? Well, the answer is that at Kilauea, much like these other volcanoes, this process happened incrementally in a series of collapse events. So this is, again, a map of the summit, and that red shaded area is roughly denoting the area of the collapse. And what we observed happening is that 62 times over the course of the summer, that central caldera area, which gradually enlarged, but generally that central caldera area would drop downwards towards the magma reservoir, and it would drop potentially by as much as meters. Meanwhile, interestingly, the ground around the caldera would actually move upwards and outwards, and this would take place over a span of just seconds or tens of seconds. So that's a little bit paradoxical. So the inner part is dropping, and the outer part is moving upwards and outwards. These blue lines actually denote measurements of GPS displacements during these events, and they show that general pattern of outward motion of ground around the caldera. So what we think was happening is that as magma was withdrawn from the reservoir, again to feed the lower east drift zone eruption, that gradually destabilized the rock over the reservoir. And periodically then, that piston of rock would slump downwards into the reservoir, and it would actually pressurize that magma. That would cause, so there's the piston dropping downwards, and that would cause upwards and outwards displacement of the surrounding rock. So you get downwards motion above it and outwards and upwards motion around it. Interestingly, that also gave rise to another really neat observation from the eruption, and that is that when these collapses happened at the summit, we would actually see surges in eruption rate 40 kilometers down the rift. So again, that's consistent with this model. The rock collapses into the reservoir and pressurizes it, and that actually pushed magma at high rate down the rift. So a pretty remarkable observation. So why does all this matter? Well, again, as I said, caldera collapses, they can be really hazardous, but very few have been observed. This is just the 8th observed since 1900. As I said, the events really shed some interesting light on magma storage conditions, the causes of reservoir failure, and caldera collapse mechanisms. All of these things are in fact poorly understood, but have some really important implications for hazards and for basic science. And then finally, I think understanding what happened this summer in 2018 should give us insight into what's going to happen in the future. So going forward, what happens next at Kilauea, and also has implications for interpreting data from other volcanoes from around the world. And since we all like numbers, I'll leave you with this final slide, just summarizing some of the key statistics from the Summit eruption. The total collapse volume at the summit was about 825 million cubic meters. If I did the math right, that's about 300,000 Olympic-sized swimming pools, which is still a huge number that's difficult to understand intuitively. There were 62 of these collapse events. The total vertical collapse was more than 500 meters, so an enormous vertical change. The tallest ash plume was 30,000 feet. And I didn't mention this much, but during each one of these piston collapse events, there were cycles of increasing earthquakes. And some of these cycles had more than actually 700 events. So that's all I have, and I'll turn it over, I think, to our next speaker. Thank you.
Great. So I'm Adam Soule. I'm a scientist at the Soule Oceanographic Institution. And Kyle mentioned that Kilauea is probably the best monitored volcano in the world, and all these eruption events we got to see in real time, and that's fantastic. But what I'm going to talk about is what's happening beneath the ocean surface. So large part of this volcano sits beneath the ocean, and those areas were impacted by this eruption, and it's a part of the volcano that we don't monitor nearly as well or have as many observations on. So just to give you a summary of what I'm going to talk about, we did some seafloor mapping offshore from the site of the rift zone eruptions that Kyle mentioned, and used that mapping to try and constrain the volume of material that was deposited in the oceans, and both the mechanisms of deposition as well as the implications for the hazards associated with those coastal areas. So to give you a little bit of a summary of the rift zone eruption, as Kyle mentioned, it's 40 kilometers from the summit, and it began erupting on May 3rd and erupted for roughly 3 months. There was about 450 million cubic meters of lava deposited on land, and that is the largest eruption on the flank of Kilauea in the last 200 years, as Kyle mentioned. It's also the most destructive eruption on Kilauea in the historical record. There were 700 homes or so lost and thousands of residents displaced. There was more than a square mile of new land that was added to the coastline during this event, and an ocean entry that was more than 3 miles wide in a spectacular display where the lava entered the ocean, causing plumes of steam and explosions. So to give you a sense of where this study that I'm talking about was occurring, we're kind of spinning around the big island of Hawaii. You can see the Pu'u'o'o eruption, which was active for around 35 years, and then further down the rift, the lava flows from the 2018 eruption. So using the research vessel Nautilus that's operated by the Ocean Exploration Trust in a project that was co-sponsored by the National Science Foundation and the NOAA Ocean Exploration Program, we conducted some bathymetric mapping out to probably water depths of 3,000 to 4,000 meters. The most interesting part was near the coastline, and in this view, you're looking at the difference between the newly mapped surface and a surface that was mapped in 2006. So where you see areas in red are areas where new material has been added to the seafloor. You can see in this image that where the new land was built out on the coastline are the same areas where you were building these deltas of volcanic material down in the ocean. So ocean entries are well known as a particularly hazardous area on ocean island volcanoes. My colleagues at the Hawaii Volcano Observatory are not known for hyperbole, but if you look at some of the titles from their weekly newsletters in the past, it really opens your eyes to how serious a hazard can occur at the coast. When you have the lava and the water interacting, you can produce explosions, you can produce toxic and corrosive plumes, and you can have catastrophic collapse of these benches and deltas that are built out during the eruption. In fact, as I understand, the 3 deaths that are attributed to the 30-plus year Pu'u'o'o eruption are all related to ocean entry events. So one of the interesting things that we found is that during the deposition of lava in the subsurface, we modified the seafloor significantly. So the seafloor was at a slope of around 15 to 20 degrees, and this new material steepened that slope up to 30 degrees. That's the kind of information that's going to be really important for looking at what the mechanisms are that cause these catastrophic collapses. They occur pretty frequently during active eruptions, but we have a pretty limited understanding of what mechanisms lead to them, and as a result, significant difficulty predicting when and where they'll occur. In addition, we have very few observations of what the deltas are made of. Most of those come from shallow scuba dives during past eruptions. And we were really fortunate during this event to have a remotely operated vehicle, Hercules, on that ship that was doing the mapping. And you'll hear a little bit more about the program that was out there from Chris German, but we were super excited to be able to take that ROV and bring it over to these new lava deltas and see what they were made of. There's a much greater diversity of material than I expected to see, including fine-grained clastic material broken up either by slumping or by hydrovolcanic explosions, coarse-grained material, and even intact lava flows that traverse that 30-degree slope for more than a kilometer. So I'm going to show a little video from one of those lava flows. And on the map, you can see we're kind of near the toe of this lava delta. And these lava flows appeared, for all intents and purposes, to be flows similar to what was reaching the coastline, and but staying intact, not getting broken up by interacting with the seawater and moving down the slope. And there's a potential that these lava flows act as a kind of reinforcing member in this large pile of rubble, allowing it to maintain those steep slopes. Chris German's going to talk a little bit more about the details of what was found on these lava flows, which is really exciting. So I will end here with just a little bit of a summary to say that, this huge volcano that's incredibly well monitored has a lot going on beneath the ocean surface, and when we're able to remove that ocean veil, we're learning some really incredible things about volcanic processes that are new and hopefully will help us constrain hazards better in the future. Thanks.
Okay, so I'm going to finish out the cycle of our presentations with a discussion of, as Adam alluded to, the discoveries we made on that final dive when we went and dived on these lava flows with our remotely operated vehicle, and actually discovered new forms of hydrothermal circulation that had become established inside those lava flows that were brand new, and not only that they were actually geologically active and producing chemical enrichments in the seawater that was coming out from these systems, but that even though that seafloor was so completely brand new, it had already been colonized by microbes that were chemosynthetic microbes taking advantage of this new geologic feature. So this is work that I was conducting in the area already off Loihi Seamount, I'll talk about in a moment. And it was co-sponsored, my program was actually co-sponsored by NOAA's Ocean Exploration Program and NASA's Astrobiology Program. And so just for context to show you where I was actually working, on the left is a map from the U.S. Geological Survey of seismic activity in the area, showing about the areas where Kyle and Adam have been talking about. And then for comparison, Loihi Seamount is just here. This is a topographic three-dimensional map of the same place, showing that it's basically where the next island of the Hawaiian chain is going to be. It's a volcanically active system that was already known to host some hydrothermal activity. So it wasn't that we were actually able to mobilize everything and actually take our ship out to this area as rapidly as we could be in response to the eruption. We'd actually been planning for a couple of years to go out and study these sites because the Loihi Seamount, that's only about 20 or 30 miles away, but significantly deeper, already hosts a whole bunch of different kinds of hydrothermal systems. And so we've been interested in this for two reasons, from a NOAA perspective and from a NASA perspective, of trying to understand how the geologic processes of the volcanism in the middle of the Pacific Plate can then give rise to the chemical energy that can drive primitive microbial organisms and fly a whole ecosystem. And the reason we're interested in that is twofold. From a NOAA ocean exploration perspective, you probably are all familiar with the ring of fire around the circumference of the Pacific Ocean. This is a view of the Pacific Ocean without the ring of fire highlighted, and it just highlights everything else we know for seafloor volcanism and hydrothermal activity, and sadly, it's restricted to 5 stars. We have half of the Earth here. We know it's made of volcanic activity. These are the only places where we've been able to study these systems. So in terms of just understanding our own ocean and our own planet, it's a fundamental gap. From a NASA perspective, they've even got even more excited because it turns out that that Loihi site I was just showing you, in terms of pressure and temperatures of the hydrothermal systems of that one place we have found, is currently the best fit to the stuff that you've probably did press releases last year and years before of evidence for seafloor hydrothermal activity, which may also produce a habitable environment that may or may not be inhabited on Enceladus, one of the moons of Saturn as revealed by the Cassini mission. So there's a lot we didn't know about this area. But the reason we went there was in the spirit of exploring new places and new kinds of things that we haven't had the opportunity to study on the seafloor before. And so, of course, it would have been perverse when Kilauea started erupting and we had all these great things happening there that we wouldn't join in as well as understanding the ocean entry system. And so it was a really great opportunity that we were using telepresence as well. So as Adam started processing his bathymetry and came up with really interesting results on how the seafloor shape had changed, we were actually able to rope him in from shore so he could actually co-lead the dive with me, that we can actually go and allocate a dive and head over to that ocean entry site. So then again, if we can turn the sound down, please. We don't need any sound on the video. Somebody at the back there can mute the computer. Okay. All right, well, you'll have to bear with me talking over myself because you'll hear narration. The trouble with a telepresence narrated operation is that people talk all the time. So this is us launching the vehicle. We started off, we were studying at around 300 meters deep, and then we went down to about 1,300 meters deep and started working our way back up again. And it was about 800 meters or so up was when we actually found this volcanic, this intact volcanic flow that we started following upslope. And this was basically, so Adam was having a lot of fun looking at the volcanology of this system for quite a long time until suddenly this bright yellow stuff came into view. And then as chief scientist on the ship, I kind of stepped in and said, okay, I'm taking back over the dive now because this is the stuff that I came for. And it was a roll of the dice. There was no reason why we should have expected there would be hydrothermal activity that would be alive within this first 100 days maximum. But if you keep your eye on these yellow systems here, we're going to zoom in on them from a distance. We could see them from color change. The geochemists on board were excited because we could tell, well, that must be a different mineralogy and hydrothermal flow, and probably it's all extinct, but there's no requirement that this flow is still active today. The lavas may have just been quenched very quickly. But as we zoomed in, we started seeing around the edges here, these little flanges. We could actually tell that they were actually quite gelatinous and flexing. As we zoom in, you can see that. You can see there's stuff wafting around here. That was not a mineral precipitate. We started to believe, okay, this is actually life here. This is something that's actually gained life. And as we pan across to the left here, we then actually began to see active flow in this area under this crevice just here. So we very quickly, we had all the right kind of equipment on board the ROV it wasn't that we expected to find this stuff, but we knew how stupid we'd feel if we didn't equip ourselves for it. So we were actually able to take down these special gas-tight samplers that can actually extract material. They can work to much higher pressures and much higher temperatures than they needed to. We were able to put this snorkel in. We were measuring this fluid. It was only a few degrees above the ambient background temperature. It was 7 to 8 degrees Celsius compared to the 5 or 6 degrees you'd expect. But we were able to draw out water samples. We did some preliminary analyses on board ship. They show some of the characteristics are very rich in iron, similar to the things at the Loihi seamount 20 miles away, but also those sites at the Loihi are about 500 meters deeper. And then once we'd done that, we then also had a different snorkel system for the microbiologists, and it basically just slurps stuff through this tube, and then it goes through a coil, and you'll see it every now and then on this last final little bit of clip. You'll see some of that material. So we don't have the results on the microbiology yet, just that we have the microbes and that we've sampled them and then we've brought them ashore and we're going to be working on that. So that's basically it. We know, as Adam was saying, the eruptions only started in May. They entered the ocean by mid-May. We were actually there at the very end of August, was the very last point when the ocean entry happened. So it was disappointing to have kind of missed out on all the volcanic activity that these guys were excited about, but it also was what made it safe for us to be able to take the ROV in and go and dive to the seafloor within 10 days and go to this area. And the really important thing then is that we had this interesting hydrothermal field that had already been colonized. So the microbes somehow from somewhere had already got to this site and colonized it within that 100-day window, or maybe much less. This was only the top few meters we were looking at of a seafloor that's shallowed by over 100 meters since the start of the eruption.